I think Rakesh probably hasn't met Shoaib.
Good. Yeah.
So just like a so for everyone who doesn't know Shoaib, so Shoaib is a professor in Turkey, and
Mm-hmm.
he specializes in signal processing and cognition, communications, information theory, and brain sciences. And he's currently a visiting scholar at MIT. Uh, he's done his PhD from University of California, San Diego,
Mm-hmm.
and is a part of many institutions, including MIT, and has many journal papers and patents to his name. And so Shoaib has very kindly agreed to give us an overview of EEG. And we've been using EEG with Prakash's patients for a long time, but we would love to hear your thoughts on it. And, towards the end of the meeting, maybe we can have a discussion on how we can optimize the data collection, for the way we are doing it here.
Mm-hmm.
Uh,
Mm-hmm.
for uh, so we can sort of save on some time there. So those are some things we would love to know from you and hear from you, but please feel free to start.
Sure.
Thank
Yeah.
you
Of
so much once again for taking the time to
course.
share
Of course.
your experience.
Time. Um, so as Preeti said, today's talk is going to be about EEG and EEG analysis, and I didn't know what the audience was expecting, so I put together these slides just to guide, someone who is quite new to the area. And so I made myself, I forced myself to put lots of pictures and less words, but more pictorial representations, just to show someone new to the field, what we expect from EEG, like a kind of a general overview of EEG in the first section. And I'm not sure because this is more than 100-page long presentation, so I don't know how much I can cover with respect to the content that's covered here. So you can also feel free to interrupt me anytime because I want it to be more interactive session rather than me always talking. Um, and also, in addition to everything that I present here today, I want to actually go through. I don't know how many of you guys already have MATLAB already set up in your local computers. It might be a good idea to, do some, maybe get our hands dirty, with respect to the concepts that I'll be covering today. It might be a good idea to run some, real data sets on MATLAB. Um, I mean, I
So
would lot of things, but I don't know how much time. I mean, time is limited, and I don't know which ones I should cover. Or maybe we can have another session just to cover the practical, aspect of EEG analysis. That might be also okay with me.
that seems to be a good idea. Like we can cover something, and then of course all of us have MATLAB, and so we can like do some practical implementation as well. So
Okay.
leaving it up to you, like we can start off with the basics, and the more involved parts we can have either another session, or
Sure.
you can just stop wherever you and we'll pick it up next time, next week or next to next
Okay.
week whenever.
Yeah. Talk about that. Okay, so let me just go through my slides and please, again, interrupt me anytime you like. If you have questions or if you've got something, a comment, for example, that you would like to make. So this is all informal session. So first, before I start, I mean, there are many contributors to this slideshow, and some of which I already summarized at the bottom of this slide. But it's quite extensive, the people who have contributed to the field, and also I borrowed lots of material from these contributors. Some of them are here, but most of them are not even written. Some of them are in the other slides. Their papers, their books, or some review papers. My original objective with this presentation is just to make sure that based on, like, if I've got these nice quotes from this paper by Bechtel, who wrote in 2014 that what you're able to see depends on your training. So my objective is again to improve our training with EEG so that by just looking at the available signals from brain, we will be able to tell what's happening, right? That's the main idea here. But I want to start with some useful facts about the brain. Some of you guys might be already familiar with these statistical information, but we would be mostly worrying about cortex. And the thickness of the cortex is about 1.5 to 4.5 millimeters. There's a total area is 2,200 centimeters square. There are 10 to the 10 neurons with 75% of excitatory and the rest is inhibitory. And synapses and neurons are around, like number of synapses is 10 to the 3 to 10 to the 4 per neuron. And the length of connections of these neurons are 10 to the 7 to 10 to the 9 meters. If you just put them, concatenate them one after another, that will actually be enough to cover 2.5x distance from Earth to Moon. So it's a pretty long way. And the ion channels per neuron actually varies between 100 to 1,000, which basically allows us to exchange of information, both electromagnetic context and or chemical context. And so I want to just go through this slide because this is going to give us an overview of what are the available signal acquisition techniques from the brain. And these activities, like brain activities, could come actually in different forms, such as magnetic or metabolic, such as the blood flow, the optical or electrical. And there are different recording techniques, such as MEG, fMRI, EEG, or the cortical ones, such as the invasive versions of these electrical signal acquisition techniques, such as the ECOG is one alternative to EEG. You can see that the MEG and EEG are maybe the most pervasively used techniques in the field. And they are non-invasive, meaning that you just hook up some electrodes on the scalp of the brain to collect information. In the invasive versions, you basically usually increase the signal quality. I'm going to be focusing on the EEG, which is a non-invasive technique. It's going to be based on electrical signals. And most of the time, you will have a task that the brain create those potentials based on the task and what we call brain waves. They're going to be recorded, amplified, and digitized, for further processing. And here is a simple summary of comparison, basically, of the different recording techniques and their advantages or disadvantages sides. For instance, EEG is low risk, low cost, high portability, highly portable, high temporal resolution recording technique. However, its spatial resolution is low, and signal-to-noise ratio is also low. As I said before, since it's non-invasive technique, you have only limited communication with the neurons in the brain, on the cortex or in the stem, which basically propagates through volume conduction to the surface of the brain. But EEG, as you can see, compared to MEG, for instance, or fMRI, has lots of compelling features, and I think it's worth to study the analysis because it's low risk and low cost, basically, compared to MEG and fMRI. What is EEG? EEG is essentially a measure of neuronal synchrony that the neurons in the brain creates when these neurons are stimulated. It creates a potential, but unfortunately, it's too small to be measured by an external electrode on the scalp. And in order to focus on these EEG important neurons, they are usually aligned vertically. We have to use amplification, for example, to amplify these too small or maybe low power signals to record. And these are this EEG is generated by a huge population of neurons. It's not a single neuron. It's a population of neurons, and we collect, their collective behavior, okay, in the signal domain. This collection of multiple neural signals, they usually come in either constructive or destructive ways, because these waves can actually add up in constructive or destructive manner. And the idea with the EEG analysis is to try to understand maybe not a neuronal level, but a population level behavior of these patches of brain. Okay. So my talk is going to be structured the following way. I will start giving you a brief history of EEG, and I'll try to motivate why we use EEG. We'll talk about the basic physics, and then the data collection process. I'll mention the challenges in the EEG analysis first, before I start talking about the analysis. I'm going to divide the EEG analysis into two components. First component is pre-processing. Although it's easy to articulate the pre-processing, but there is a huge pipeline behind it. It's mostly standard, I would say. So it's kind of easier to cover. However, the post-processing pipeline is not that easy because it's task-dependent, the objective-dependent, hypothesis-dependent. Therefore, we will have to probably cover the post-processing analysis of EEG signals, maybe in another session. Today's talk mostly going to be focused on the pre-processing pipeline, and maybe give some pointers to the post-processing analysis of EEG. What are those post-processing options? For instance, the event-related potentials. We usually use these response averaging. And in addition to that, you can run time frequency analysis, what's happening in the time domain as well as in frequency domain. Another alternative could be classification analysis. If you focus on two, for example, competing mechanisms in the brain, and you see how separable these mechanisms are from the EEG signals. And finally, the connectivity analysis, which will provide us the understanding of the different regions of the brain and how strongly connected they are as a function of time. Maybe the most significant impact of EEG has been in the field is its temporal resolution, which I'm going to probably discuss it maybe later in my presentation. But EEG has huge potential for temporal, what's happening in time domain, in time axis. And therefore used, for instance, in conjunction with fMRI data to have both time resolution and spatial, good spatial resolution and good time resolution. Anyway, when you look back in the history, I think one of the oldest EEG observation could go back to 1875, when Richard Caton observed the EEG from the exposed brains of rabbits and monkeys. Later on, the following years, 1912 or 1914, these people actually published papers, and they indicated the EEG recordings of experimentally induced, for example, seizures, mostly from mammalian creatures. But these 1912 and 1914 actually marked the beginning of utilization of EEG for both humans and animals, for understanding what's happening with respect to the impairments, like brain impairments. Later years, 1994 and 34, there have been interesting applications of EEG, such as radio equipment is used for amplification of brain signals. And in 34, Adrian and Matthews verified the concept of human brain waves, and they identified regular oscillations around 10 to 12 hertz, which they named it alpha rhythm. So the name alpha rhythm goes back to 1934. And we also use, as some of you might know, alpha to characterize how much we are attending to the stimulation. So this is probably like marking 100 years old concept in the EEG field. And why do we measure EEG? As I said before, the greatest advantage is the temporal resolution. EEG can determine relative strengths and positions of electric activity in different brain regions. And there are many applications. Most of them are clinical in humans and animals. They include, I tried to here list some of them, and the one that we're probably most interested in, not necessarily clinical, but monitor, for example, attention, monitor, for example, human brain impairments, when people's are coma or seizures, for example. Idea is to just test afferent pathways, for instance, through evoked potentials. Understand, for example, the root cause of these issues. And yeah, many more. And I've listed here, so I don't want to go through them one by one. But it's a very useful modality. Here are some other, current neuroimaging modalities. I've picked 4, and in all modalities, maybe except EEG, the sensors are quite weighty. They're very heavy to carry around, and in many of them, except EEG, you have to be stationary while the signals are collected. For example, in functional fMRI, you use this huge device, and you are supposed to stand still while this device is capturing signals. And positron emission tomography is the same. MEG, for instance, as you can see, also requires you to not move your head. But in EEG, it's more flexible. It might be the only modality that doesn't necessitate the fixation of the head and body. It also holds the potential to monitor the brain activity of individuals engaging these routine tasks in workplace and home environments. In other words, the mobility can allow EEG to have extensive applications, such as gaming, for instance, where you may use your head to move in the two-dimensional, like simulated three-dimensional world. So this lack of constraints principle in the EEG makes it a very powerful tool for future envisioned applications. But of course, there is a downside of this technology, because it would create, since the SNR is low, signal-to-noise ratio, it creates a lot of artifacts, and therefore you have to have sophisticated set of principled pre-processing and post-processing algorithms that you need to apply to signals to extract the source signal from the brain. These couple of slides here, they're talking about how the EEG signals are generated in the brain. The neurons are activated, but how? There are local currents that are generated as a result of a stimulation. And the EEG measures the current that flow during the excitations of dendrites of many pyramidal neurons. Pyramidal neurons are the most populous members of the excitatory family in the brain area. And these potential differences are caused by accumulated postsynaptic potentials from pyramidal cells that eventually create these dipoles between the soma and apical dendrites. So there are 2 necessary conditions here. One, aligned neurons. Neurons need to be aligned, and the synchronous activity. As I said before, EEG is not supposed to extract information from neuronal level. it's intended to capture signals or data from population of neurons. Therefore, when the population neurons start synchronizing with each other, then it can provide the useful information for EEG, which is a crude representation of what's happening in the brain. Here's a simple picture to show you, how the neurons are excited, and then they create these neural synchronies. And then through volume conduction, we were able to capture the signal, from a single scalp electrode at the top of the skull. There are many manufactured devices to successfully acquire EEG, and you have to be careful about the caps, conductivity gel, ruler, just to measure the scalp, injection like we use syringe, for example, here and downstairs, and of course disinfection is another component of the EEG acquisition. The equipment has amplification unit because, as I said, signals are quite low power, and PC, laptop, and of course the software. So that through the software you can collect the signal, visualize the signal, and that can actually give you an idea about how the signal looks like before you start recording EEG. Here are top 10 EEG hardware companies by the year 2017. The three most important ones are Neuroscan, which is established in 1985. Again, at the time of 2007, I've been able to count over 10,000 publications that mentions Neuroscan. There are also two other major key players in the field: Brain Products and Biosemi. These are also established in 1990s companies, and a total of more than 10,000 publications for both that you can see in the literature. Some of them are, focused on more portability of the EEG device manufacturing. Some of them are like more quality, like less. A better SNR is their vision in their business plan. So it depends on your application, your objectives, which one of these might be the most suitable alternative for your own business or for your own experiments. The EEG electrodes can be modeled using RC elements. RC meaning register and a capacitor circuits. And I don't want to dwell on this, but what I'm trying to say is that what happens here, if you model what's happening between the electrodes and the currents that are flowing in the neurons, inside the brain, you can basically have these components of RC blocks of circuits that helps you extract that data. Okay, that's the bottom line here. And most of the time, one of these RC components dominates the others. So you can actually simplify this circuit by a single RC. Here are some of the, for example, silver chloride-based electrodes, which is far left. And you have dry contact, insulated, non-contact, different types of electrodes. And they can be modeled using the same idea, using RC circuit. The beauty of the RC circuit modeling is that the capacitor is able to capture the power and store it for some time. And therefore, that storage helps you to extract, for instance, if you're quick enough, extract the signal. Because if, for instance, stimulation in the brain disappears, that capacitor already has stored, the past data. Past meaning maybe a couple of milliseconds ago. Okay, so that's actually modeling the propagation of the signal inside the brain, and that's why we're able to, extract the EEG signal from the scalp, although we have got many layers, before we get to the source in the brain.
So is this modeling is done by the company who is providing the things, or is the people who actually model?
These are like literature. Most of the people in the literature modeled these different layers. You see the coupling layers. They try to explain how or why EEG works. They come up with these RC circuits to explain the coupling between the layers. I don't think that companies necessarily use it to promote their products. Yeah. Let me just jump to the practical design considerations. So to be able to, get the high quality signal from electrodes, you have to have a contact resistance. Okay, the contact resistance of these electrodes is supposed to be between 5 to 10 kilo ohms, and if the resistance is too high, then your signal power will be very low. If it is too low, then there is the problem of closed circuit, creating a closed circuit, which means you will not be able to capture the patterns quite quickly, because it will act as a filter, which I'm going to clarify what filtering means maybe later in the presentation. But the two extremes, having a high impedance, resistance impedance, I'm going to be using these two terms, interchangeably throughout my talk. High or low impedance or resistance is both of them not desirable. And 5 to 10 kilo ohms practically is chosen to be a good acting resistance for EEG. So we employ amplifier, as I said before, with very high input impedance. The idea here is that we don't want any current to move inside the amplifier, because we would like to measure the voltage difference, right? The voltage difference is more reliably measured if there is zero current, right? So that means high impedance. And that's the design manufacturing idea behind the amplifiers. And of course, such that the skin electrode impedance become negligible. In other words, this 5 to 10 kilo ohms is still big enough for not having closed circuit phenomena, but compared to amplifier, it's going to be negligible. And therefore, we will be able to reliably measure the voltage. Oh, by the way, this one here, see on the bottom right, is from BioSemi that we're using downstairs. And yeah, these softwares that comes with the device helps you see what type of impedance for each electrode, for example, how high the impedance is, and you try to make sure that these contact resistance, because we are using gel, right, to create the contact between the scalp and the electrode. If you don't put, for instance, gel, that enables the conductivity. If you don't have enough gel, then it would actually create a high resistance, right? Because the air's resistance is way higher than the gel's resistance, and therefore you will see something like the ones shown on the figure, that you will see a bump in your screen, and that would indicate that there's something wrong with this electrode, or maybe there's a less gel than intended to be. So therefore, you have to just go and check that electrode, and then put maybe more gel, or figure out what's wrong with the electrode. Sometimes electrodes might be very old, and so therefore their resistance might, as a function of time, it may be increased. So there are different types of electrodes. The standard ones, most likely and more reliable ones, are wet electrodes, but there are also dry electrodes. And those dry electrodes are kind of more practical because you don't need to really inject any gel on the scalp, and so it's more convenient too. But of course, the flip side of the coin is that they usually provide less SNR, meaning the low quality signals for these electrodes. Here are some of the wearable EEG devices. eMotiv and NeuroSky are the most maybe prominent key players in the market. But there are many startups working on these wearable EEG devices day by day, and they're outnumbering now the market. Therefore, most likely in the future we will see many applications where we use these wearable EEG devices, maybe as part of our daily lives. I want to talk about also the montage. So we will be using something called International 1020 system. This 10 and 20 signifies the distances between the electrodes. In other words, either electrode distances are either the 10% or 20% between the Nasian and the onion of the frontal and the backward of the skull. And that's why they called it 10 to 20 system. The number of the montage is all about the allocation of electrodes on the skull, and therefore you wanna allocate these electrodes wisely to be able to make sure that you capture the activations adequately for your own purpose on experiments. Here you can see this uniform distribution of electrodes, but it could be non-uniform too. There are some people extended this international standard to 10 to 10 system as well. As the number of electrodes increased, they thought about other systems too. But the idea here is that you can see that there's this color coding in this picture to show you where exactly the brain's there's components of the brain is supposed to contribute to the EEG signals we collect from these electrodes. Here, the occipital lobe, for instance, is using pinkish color, and that goes back to the back of the skull, named as O1, O2, and OZ, where O means occipital. Here you see, for example, the yellow is used to indicate the parietal lobe, in which that you have many electrodes to capture signals from that lobe. And of course, the frontal or temporal cortex and the signals are also used, two different colors used to indicate which lobe we are collecting signals. And there's also central location, which is the boundary of the parietal and the frontal, that we call C, and those electrodes are collecting signals from that central region of the brain. We also have electrodes, by the way, not necessarily shown here, but I think I have pointers somehow here, so I just wanted to mention. You also use electrodes to for eye blinks, so they're basically close to the eye, two of them. And we also use two different electrodes on the mastoids, which are right next to your ears, actually back of the ear, the bone. Try to make sure here that we're trying to make sure that the electrode is quite close to the bone, to minimize the effects, the brain effects on the electrodes, because those mastoid electrodes usually used to reference for the rest of the signals on the electrodes collected on the other electrodes. Here is a typical an experimental setup and the room. Most of the time we use, for instance, you know, acoustically isolated chambers to be able to collect EEG signals that the brain is not affected from, for instance, from external stimulation, because that can create, as I will cover later on in my presentation, the brain activities are really hard to single out. The electric source, the sources of the sources of electric signals that we are interested in, because we believe they are task related, it needs to be isolated from the rest of the other brain activity that can be stimulated due to other external factors, or maybe our thoughts, right? Or maybe other, brain stimulation that we generate ourselves. So therefore, these chambers could be a good technique to isolate the brain from the rest of the other stimulation, potential stimulation sources that exist in our environment. So here we use silver chloride electrodes, and there's a shield, electromagnetically shielded recording chamber, and there's a monitor where we present a visual stimulus, and the subject, depending on the task, could press a key just to respond, you know, if there are any questions on the screen. And there is sometimes we use fixed chin rest just to fix because, you know, in any case, moving the head is going to create muscle activity, and therefore it will actually contaminate the EEG, resulting EEG signal. So it might be a good idea to use a fixed chin rest, but it's not mandatory, because I'll talk about later, there are techniques to find out these EEG components that are due to muscle activity, and that can be let's say isolated from the original source that we are after. Okay, maybe I could skip that. Okay, so far, do you have any? So I just tried to give you a brief summary about the EEG systems, and before I move along with the analysis part of EEG, if you have any comments or any questions, I will be more than happy to respond now. If not,
yeah, well, another advantage of EEG is that you don't need electromagnetic shielding, which is very expensive and is involved in, for example, MRIs. But you need mu metal shielding. It's extremely expensive, and EEG needs electrostatic isolation, but that's about all.
mm-hmm. Yeah, totally right. Okay, so let me just give you this. Don't be intimidated by the crowd. It's my bad. The crowd, because I just didn't want to redraw the picture. I just borrowed it from my earlier presentations. And don't worry about the .m files. Maybe we can use them when we discuss how to use MATLAB to do pre-processing and post-processing on EEG signals later on. But what I want to point out here is that there are 3 different domains that we would like to analyze the EEG signals in the post-processing phase, because pre-processing phase, as I said before, is more standard, and I'm going to cover it today. But just to give you a heads up before we move on to the post-processing, maybe not today, but the post-processing techniques could be done in the time domain, frequency domain, or filtering or representational domain. And I may cover some of these techniques. Maybe I can cover a little bit of ERP analysis, the event-related potential analysis, and give you a brief understanding of why we're doing it. a little bit, maybe, if time allows. Because time is an important component for EEG. As I said before, the temporal resolution is high in EEG data, and therefore most of the post-processing, earlier post-processing techniques are based on time. And later, more sophisticated techniques have been developed in the frequency domain and in representational domain. But today's subject is going to be about pre-processing. So let's just get to it. Okay, so before I start the pre-processing techniques, I'd like to mention that the key to pre-processing and as well as post-processing is the experiment design, because you need to have a solid time locking signal in the EEG to benefit from its temporal resolution. Obviously, the experiment should have a hypothesis about or including time. So if time is not part of your experiment, then EEG may not be the right way to go. So the other thing is that you may need a large corpus of trials, particularly for ERP analysis. We will see that we will be averaging lots of signals in the ERP analysis, and therefore having a large corpus of trials could be really useful because it will allow you to get rid of noise. Noise meaning that don't think of noise as, simple independent Gaussian noise, but anything unrelated to the task could be a noise source. And therefore, this noise could come in different forms and shapes, and in terms of statistics, and that's what makes EEG analysis. And EEG signals are non-stationary signals, so that also makes EEG analysis a bit more challenging compared to the signals. Since I have a background on communication technologies, most of the time these signals are reshaped, for instance, in the transmitter before you send them over the channel. And those signals are usually very simple. And the channel introduces noise, but most of the simple channel models, for example, they create very simple statistical, morphing the signal or massaging the signal in a way that makes the receiving end, to use simple techniques to recover the original signal. However, EEG signals are not like that. And therefore, we need all these, sets of analysis tools that we are covering today. And one of the things that you need to be careful about, you need to break your experiment to short blocks and, of course, build in time for breaks. Because if the attention is lost, then EEG quality decreases. There are many softwares to design your experiment like PsychoPy, OpenSystem, and SuperLab. I think the most dominant is PsychoPy, which is based on Python. There are also many analysis tools as well, depending on your field of expertise. For example, I have an engineering background. I prefer EEG Lab or MNE in Python, and EEG Lab as a MATLAB framework. But if, for example, coming from a psychology background, there are other alternative and maybe less programmatically maybe easier analysis tools out there. So I would encourage you to look for those analysis tools that would probably minimize your, it would not require you to code, for instance. EEG Lab and MNE, for example, EEG Lab has a GUI, a graphical user interface, that which I'll show you probably maybe today. It will allow you to not code, but choose the techniques that I'll be covering today, and therefore it makes it quite easy. But MNE, for instance, doesn't necessarily have a standard GUI, and therefore you have to deal with Python code in that case. It's quite easy to download the EEG Lab. There's this link, and you can just unzip it, add the folder to your path, and it's good to go. Here's a simple experiment that we recently run at MIT. This was about a sequence of blur, sharp and clean stimulated images, basically faces. We have this particular sequence of face clear and face sharp presentations and also phase blur presentations. And some of these images repeated to measure and keep the attention. And subjects are required to press a button when they see this consecutive two images which are identical to each other. So that's kind of an experiment, for example, I was referring to earlier. You have to decide on how many seconds these faces should stay on the display, how many seconds between them, and what's the presentation or stimulation time, and all these little details. Because these are going to affect your EEG signals. If you don't allow, for instance, a good amount of chunk of time for the presentation, then you may not be able to stimulate the brain activities. Here's another example, which is based on steady-state visually evoked potentials. These potentials are generated based on repetitive evoked potentials, which is naturally produced when you view a stimulation, a flashing stimulation, between a range of 6 to 75 hertz. This paradigm is often used in brain and computer interface applications because of its high SNR, by the way, most essentially. But because if the SNR is high, then you have this ease of detection, and the amount of information that a user can communicate actually goes high. Like they measure it using information transfer rates. So that's a huge. So the SSPP has a huge potential because all you need to do is just to segregate the frequencies in the brain. Remarkably, the brain cells, when you show the brain, as a repetitive or maybe a flickering stimulation, then at some point, and maybe quickly, I would say maybe 300 to 400 milliseconds, maybe less than that, a little bit less than that, the brain cells start flickering in the same frequency. In other words, they generate oscillations. They start syncing with the phase of the stimulation, and therefore you can just look at the frequency and phase of the stimulated EEG signals to detect frequency and phase values. And those frequency and phase values, if they've tagged with one letter, in this example I'm showing you a speller application. If you associate these frequency and phase values with one of these letters, then therefore you can follow up the brain where the attention is mostly focused. By looking at the EEG, you can track the brain's where the subject is looking at, and therefore where the attention is focused. So how do we process EEG data? As I said, I'm going to have two different steps, pre-processing and post-processing. They're mostly independent, but they will affect each other, particularly if you don't do pre-processing well, then your post-processing may generate junk at the end. So why pre-processing? As I said, EEG is a noisy, extremely noisy signal, and it's likely to measure different sources that are not necessarily task relevant. And to make sense of all that, we try to extract meaningful measures. So therefore, we need to do EEG analysis. Why post-processing, which is the most exciting part? Because post-processing allows us to have higher level of understanding of the brain functions, intention, right? Cognitive abilities of the brain or other cognitive functions. For example, recently we're running experiments here at MIT to understand the spatial frequency processing in the brain. And to be able to understand, for example, where exactly these spatial frequencies are processed in the brain and for what reason, then you need to run higher level processing. You have to employ higher level processing techniques such as connectivity, for instance. Okay, so here is the general picture. that I usually employ for pre-processing. So after EEG collection, I'm going to go by, block by block here, but just to give you maybe a summary. But I have other slides that talks about each one of these blocks in detail. I don't know how much time do I have. I think it's already 1 hour. So how much extra time can I borrow?
Usually we do 1.5 hours per day.
Okay, so
I don't
maybe 20 more minutes. Maybe I can finish the pre-processing.
I think pretty
Yeah,
good.
20 more minutes should be good.
Yeah. Let's go through the pre-processing pipeline quickly.
Okay.
If you've got questions, maybe we can use the last 5-10 minutes for questions. Okay. So as I said, I have to probably have another session just to cover the most fruitful part of the presentations. Unfortunately, we couldn't get to there to be able to lay the foundational knowledge about EEG. But anyway, so after EEG collection, we import the data, and then we examine the EEG data, maybe visually, okay? So visually meaning that we look at the data, and if we need to, we can remove, for example, some of the redundant channel information. So depending on your setup, some channels may produce zero signal. Zero meaning that just a noise signal, right? It has got nothing to do with the brain activities. So therefore, you have to examine those. For example, downstairs we are allowed to collect 32 channels, 64 channels, 128 channels, for instance, but with additional electrodes, like for the eye channels, we use 2 more electrodes, and mastoids another 2 electrodes. So to be able to compensate for that, you have to add these electrodes, signals that are coming into the system with these electrodes that need to be added as a configuration file need to be adjusted to be able to get signals from these electrodes. But for example, if you look at the 1010 or 1020 system, you will realize that the number of electrodes are the powers of 2. So if you've got 64 channels, for example, already allocated for brain signal activity, and you need to add extra 4, that means you need to have, I don't know, like maybe 72 channels. But only 68 are useful, right? 64 for the brain activity and 4 others for your, processing, pre-processing or post-processing. And therefore, the rest of the other 4 need to be just removed. And therefore, you do it after importing data. You need to just remove those 4 channels because they're just collecting no data, no useful data. And then you import event markers, channel locations, which it will make more sense when we do all these in the MATLAB. And then you re-reference the signal using mastoids. If you do have mastoids, you use them. But if you don't have mastoids, then you need to use averaging, okay? Because that's the best you can do. Averaging meaning that you average the signals across all channels, and then you use that average as your reference, okay? I'm going to talk about the theory behind averaging later on in my slides, but let's just take my word granted for now. So the next step is filtering, which means we're going to have to filtering meaning frequency domain. We allow some frequency to pass and some frequency to be not pass, okay? Which means we kill them. In other words, we extract them out from the original signal. Here, when I say filtering, I specifically mean high pass, which means anything below 0.5 hertz are not going to pass through the filter. Okay, so therefore, keeping anything below 0.5 hertz is not allowed because it could be really harmful for the later stages of the pre-processing. For example, one technique called independent component analysis does not like any DC component in the signal. DC meaning that the signals could have additional data, like additional voltage, which has got nothing to do with the pattern analysis. Okay, it's just an additional 4 volts, for instance. You just subtract that 4 volts from the signal to put everything in perspective, which means the signal is now going to oscillate across 0, right? I mean, yeah. around zero, not equals, around zero. Okay, next is clean line. So most of the power lines has, you know, a constant noise. Typically in United States, it's 60 hertz, but in Europe, it's 50 hertz. And you need to clean that line, meaning that there is a bump in that 60 hertz, and you need to apply something called notch filter that will basically take that part of the signal out. And then you have to reject data. Rejection is based on artifact removal, could be based on artifact removal, like based on I channels, or identification or rejection of bad channels. So because some of the channels could be bad, it could be, it could be due to, maybe contact might be problem, or there's a problem with the gel, or the electrode might get old, and therefore create, signals that requires to be interpolated, which means that based on the other channel information, which are healthy, you can interpolate, which means the generation of new signal, and then you replace the signal in that bad channel. That's an alternative. You don't need to replace anything because, for example, in psychology context, people hate to replace data because the replaced data is a combination, nonlinear or linear combination of other signals in the other channels, and therefore it may be harmful, because it can actually hide the brain activity that you might be interested in. So it's kind of disliked in that community. But in many cases, these techniques have been improved a lot recently, lately, and therefore they could generate, using, for example, deep learning techniques, they can be quite useful for, from a completeness perspective. And next is, after this artifact removal, you resample the signal, which means downsampling, which leads to to a high pass filtering and half the resample frequency. So if you think about the signal's frequency response, the highest frequency of the signal is a limiting factor of your downsampling ratio, okay, which means resampling ratio. In other words, if you have, for example, the highest frequency in your signal is 100 hertz, for example, then you can only downsample the signal up to 200 hertz, okay, which means 200 samples per second. If you go below that, that can actually harm your signal. And I'm going to come and discuss why this is the case. This is a very basic signal processing theorem behind it. And because that's what's called something called aliasing, and I probably have a picture for that. Maybe I'll cover later on. After downsampling is also useful because you don't need to worry about too many samples. For example, the BIOS-MI we're running here generates 2,048 samples per second. So this might be way more than you need. Okay. Therefore, downsampling allows you to reduce the number of samples to process. And for example, heavy algorithms such as ICA could run on a subset of these samples. And it would actually expedite the entire process. It would speed up your processing because you're only dealing with 256 samples per second, or maybe 512 samples per second if you downsampled by 4 or 8. And after the independent component analysis, which is a blind sort separation technique, which I'll probably later on cover what that means, but what it does practically, it decomposes the EEG signal into subcomponents. Subcomponents meaning that it could be eye component, it could be muscle component, it could be the original brain component, it could be other components that are irrelevant to the task at hand. So therefore, ICA is a very useful technique, but of course there are assumptions behind the ICA technique, which I'll cover later. But ICA is maybe the most dominant. I think it's invented in 1985. It's the most dominant technique and frequently used technique in the EEG analysis. After ICA, after identification of these components, you reject some of these components, meaning that you take out these components from the signal, and that will allow you to have a cleaner waveform, okay? And I'll probably have some pictures to show you that, how the signal looks like before and after these rejection of these independent components. And finally, after the ICA, you have extraction of epochs. Epochs are like time segments, time signal segments. Here, for example, you can have starting from 200 milliseconds before the onset, and then you have maybe 1,000 milliseconds after the onset as your segment, data segment, which we call epoch. And we extract these epochs based on the events, right? For example, in our experiment here, we have blur phase, clear phase, or sharp phase. Each one of them are basically triggers. So they are labeled triggers in the data, and you know where they are. And therefore, these are treated as the onset of each stimulation. And they have different types of these stimulation. And you focus on the onset and then take 200 milliseconds before that and 1,000 milliseconds after that to have your data segments, okay? And you may ask, what happens to the rest of the data? We basically throw it out. We only focus on these epochs, okay? And finally, you get these all epochs. Actually, basically, this is essentially the end of the pre-processing, because now your data consists of maybe hundreds of these epochs, but these epochs are not the same type, right? Each one of them represents one specific condition. Maybe a couple of them represents one specific condition, depending on your experiment. For example, in our case, we have 30, 40 trials or epochs, let's say, for each condition. For example, phase blur, phase sharp, phase clean. Each one of them may have maybe 100 different epochs, right? 100 different epochs. Okay, and since these are time-locked events, you can actually average them. Okay, that's the post-processing part now. Okay, so we prepared the data tensor meaning that maybe 4-dimensional data, and 4-dimension is for example, number of, it could be actually even maybe 5-dimensional, but it's going to be like number of epochs, how many epochs you have, how many conditions you have, how many samples you have for each epoch, right? And how many subjects you have, for instance. Okay, so after the epoch extraction, then you have this tensor, and then you continue with the post-processing. So I would like to make a couple of comments here. First of all, this pipeline is not always fixed. Okay, you can change the order depending on your signal. So unfortunately, there is this manual touch here. For instance, the rejection of data can cause, so here, let me just tell you this. ICA and rejection of data blocks basically serving almost the same purpose. Actually, they could serve the same purpose, because the idea in both of these blocks is to get rid of what's not necessary, right? So rejection of data can cause, for example, the subsequent ICA to work, may actually cause ICA to malfunction. Because ICA is one of the assumptions behind ICA is that the signal sources that generated these EEG signals are assumed to be independent and non-Gaussian, okay? But if you reject the data, it can actually cause, for example, particularly if you do interpolation, right? So if you reject that channel and then you interpolated that channel, right? That means you introduce dependence on your EEG signal, okay? So that dependence is going to cause a problem with the ICA, because that's a violation of ICA's assumption, okay? So this is one type of, for example, connection between these blocks. They're not independent of each other, and they can actually influence one another's performance. And for example, one other thing, for example, you might be careful about, if you, for instance, apply a high-pass filter after low-pass filter, if you apply a low-pass filter after high-pass filtering before you clean the frequency, clean line frequency, then this can typically done I mean, that's legitimate. However, that can cause very high frequency components of the signal to be lost. Okay, so if you don't know, what's important in your signal in terms of frequency, then it may be advisable to leave the high frequency intact, okay, without filtering it with a low pass filter. How many minutes do I have? Maybe 10 more minutes? Okay, so let me just skip that one. Here is the electrode locations, as I said before. So I'm going to go back to this slide every now and then, just to point to where we are. So as I said, after importing data, we examine the data, and if need be, we remove the redundant channel, but we import event marker and channel locations. Okay, channel locations is very important because it would tell you where the electrodes are, because software wouldn't know where the electrodes are. Like, you have to map the physical reality to the simulated reality. So here you see the electrode allocations of 32 plus 2 electrodes on the left, and on the right you have 64 plus 2 electrodes. Plus 2 coming from the mastoids here. I use P10 and P9, but some other layouts could have different locations. For example, here. Okay, so that's why it's important. You have to make sure that your electrode allocation on the skull and the cap you're using, because cap determines where the electrodes are. So therefore, the cap you're using and the channel location file you use for the software, they have to match. Okay, that's one caveat. The other one is, maybe I can just skip this one. The other one is of course, visualization of the signal, right? Here, for example, when you look at the typical EEG signal of 32 plus 4 channels, you see the channels are named from top to bottom, but the last 4 are 4 eye channels, like IO1 and LO2, left eye and a right eye. And M1 and M2, these are the mastoids I was referring to earlier. So these are the last 4 signals are just for your pre-processing purpose. The rest of them are the data channels, okay, which is 32. And you can see that the blue line, green line, and red line, these are event markers, okay? As I said before, when you design your experiment, you create triggers in your experiment, and each trigger corresponds to one of these event markers. And we use different colors for different events, although they name C in this case, but they usually are, you can name them, to make sure that the labels are more semantically meaningful. So
our messages are different for different students.
yes,
Yeah.
yeah. But you can rename them later on. So you can name them in your experiment, or you can rename them after your experiment. I think it's important to have different names that are meaningful, not just the color. So it's a good practice to have them renamed. So if you just stack up the EEG signal, you will realize that there are some, the signals is not, even if you stack them, the signal is not going to oscillate around the center, right? There are some blobs, and those blobs are usually, not always, but usually due to idlings. And those idlings need to be, taken out of the signal or extracted away from the signal. You can also plot all electrode signals, on top of each other to see the signal, just to understand the signal quality, basically, because you would expect the oscillations to become wild at least after 90 or 100 milliseconds. Okay, after 90 and 100 milliseconds, if you still see your signals are quiet, then there might be something wrong with your EEG, or maybe the software or your experiment itself. Okay, as you can see, before 90 milliseconds, the signal is quiet. I mean, quiet, and also looks like more like a Gaussian type noise. Okay, which doesn't necessarily mean that there's nothing going on in the brain. It is just an accumulation of irrelevant signals that come together. And you may know from basic statistics, there's something called central limit theorem. And central limit theorem basically states that if you have multiple random variables, but they are not necessarily distributed Gaussian, if you sum them all, you will realize that the sum is going to converge to a Gaussian. That's why I said it looks like a Gaussian noise. So all these activities, irrelevant activities, can sum up to something close to Gaussian. But after 90, 100 milliseconds, then you start seeing these fluctuations in the signal, which may be telling us something important. Okay, you can, instead of just plotting them on top of each other, you can also plot them based on where the electrodes are. So therefore, you can see the signal activations as a function of space, right, rather than time only. I know that I said EEG signal is bad with respect to spatial resolution, but with these different and sophisticated analysis techniques, you can increase the spatial resolution of EEG, although estimation of the source signals in the brain is still quite challenging and not necessarily reliable. But you can still see the activations, maybe a crude representation of these real activations in the brain by just looking at the signals or distributing these signals where they're coming from, okay? Because as I said before, and probably I'll mention them later on, F4, think about F4 and F6, they're close to each other, and they may be representing the same source signal. Okay, because they're kind of close to each other, and the source might be feeding. So the source meaning that the neuron population inside the brain, maybe close to the cortex, could be feeding these two signals at the same time. Okay, that's something undesirable because we want to find independent sources in the brain rather than the dependent sources, right? So it's quite challenging to single out these sources by just looking at the EEG signal, unfortunately. That's why when people say the spatial resolution of EEG is low, that's what people refer to. People say we don't have access to what's happening inside the brain, and we only have the scalp activity. It's not reliable to just base our findings, spatial findings, on the EEG signals. But you still see maybe a rough representation of what's going on across the brain by just looking at the signals, per electrode. The line noise removal is, as I said, might be very, very important because if, for example, in our case, we didn't really care about line noise removal because we have a acoustically isolated chamber downstairs, and it basically isolates everything from the subject, including the line noise. But if you run experiments without the chamber, then you need to worry about these 50 hertz or 60 hertz line noise, which is due to power lines, right? And the common approach to that is just to use a bandpass filter to remove these 50 hertz or 60 hertz concentrated line noise. Fortunately, there's an EEG Lab plugin called CleanLine. It implements a sinusoidal detection. Particularly it's a notch filter, meaning that particularly optimized for 50 or 60 hertz. It's based on techniques like noise fusing multitapering and Thompson F statistic. Don't worry about them, but what I'm saying is it's intended to remove the sinusoidal signals, particularly at these specific frequencies. One example at the bottom of the slide shows you if you use only a high-pass filter at 0.5 hertz, for instance, this is what you get as the power spectrum of the signal, okay? I don't know if you're able to see my cursor. Please tell me if you don't see it.
We see it, so I think they can see it.
They see it, okay? So here, for instance, this is the power spectrum of the signal with the line noise at 60 hertz. You see this bump here? That's the line noise. And if you apply 0.5 hertz high-pass filter with 50 hertz low-pass filter, as I said before, you can apply low-pass filter before cleaning the line noise. But that's what you get. You see, even the line noise is 60 hertz. Applying a 50 hertz low pass filter is not going to take away this bump completely, okay? Because the filters are not ideal. You can see here one specific filter I'm showing you with a pass band of maybe the cutoff frequencies is around something little larger than 0 and around 20 hertz is the other cutoff. You can see this sharp drop in the frequency response of the filter is not necessarily practical. The practical filters usually have, you know, a cutoff that's kind of gradually decreases the power, the amplitude of the frequency response. That it goes gradually. That's why you're seeing this bump, you know, kind of decreased. The power of that bump decreases, but it doesn't go away. So the best way to approach to this problem is to clean the line using a specific bandpass filter called notch filter, just to clean that 60 hertz. And that's what you get after cleaning that specific noise. Okay?